Hello, we present deep structured reactive planning. Suppose a self-driving car wants to do a lane merge on this busy road. Existing autonomy systems tend to separate prediction and planning into two sequential steps. First, the SDV would perform motion forecasting, which predicts all surrounding vehicles will move forward. Based on these predictions, the SDV reasons that if it plans a lane merge, it'll collide with the other car. Yet, a human driver might be able to lane merge by nudging inwards such that the neighboring vehicle slows down to make room. In this paper, we consider a joint prediction planning system where we account for actors' reactions to our plans. Now the SDV predicts that given its considered trajectory, the neighboring actor will slow down in a gradual fashion, making room for the SDV to merge in. We call this reactive prediction and planning, taking into account the reactions of other actors to the SDV, in contrast to non-reactive planners. There's a wealth of prior work in behavior forecasting, planning, and learnable end-to-end models. However, prior works on specifically modeling reactivity tend to assume handcrafted predictions and costs. In our work, we propose a reactive planning objective based on a deep structured model that unifies prediction and planning. We use a realistic trajectory sampler to sample k discrete trajectories per actor, which allows us to learn a probability distribution over these trajectories using a deep structured model. The model assumes two energies, a learnable energy specific to each actor's individual trajectory and an interaction energy between actor pairs defined over collision and safety distance. From this model, we define our reactive planning objective. This objective contains a conditional prediction model conditioned on the current candidate SDV trajectory and planning costs. Both of these are derived from our model energies. We demonstrate that our reactive model outperforms the traditional non-reactive planner and baselines across many complex simulation scenarios without increasing collision rate. So let's take a look at some videos where the SDV is in green and the goal is in cyan. In the reactive case, the SDV is able to take decisive action and complete the lane merge, while the neighboring car slows down to let the SDV pass. However, in the non-reactive case, the SDV is indecisive and slowly drifts to the left lane, forcing the neighboring actor to stop abruptly. In this example of a turn, we first want to note that this scenario was initialized from an expert driving sequence, and the expert also performed a turn while the oncoming vehicle was braking. While not perfect, the reactive model similarly follows the expert in successfully executing a turn in front of the oncoming vehicle. Meanwhile, in the non-reactive case, the SDV is again indecisive. It eventually gets stuck and is unable to advance any further. More examples are found in our paper and supplementary materials. Thank you for your time.